lesson 71. Okay, first let's remember something. Remember exponential functions and logarithmic functions. These are what we've been looking at lately. But remember, they're related to each other, right? They're like two sides of a coin, kind of, sort of. Is that what I want to say? Well, they're inverses of each other is what I really want to say. So if you have an exponential function like this, 2 to the x, this, you might call this an exponential function with the base of 2. And here's a logarithmic function. Log base 2 to the x, a logarithmic function with the base of 2. Remember that these things are related, strongly related, because they're inverses of each other. They're inverses. If I were to stick 3 into 2 to the x, I would get 8. If I then take the 8 and plug it in here, I get back my 3. In other words, that's what we mean by inverse functions. One does the opposite of the other. Anyway, since they are so strongly related, it means kind of two things. For one thing, it means we're going to look at both exponential and logarithmic equations on the same day. That's what it means. But it also means that a lot of times we'll use logarithms to solve an exponential equation and vice versa. So we're going to see that in action right now, right from the start. Let's start with exponential equations. And I got a couple different tricks you might use. And one of the tricks, especially if you have 10 to a power or e to a power, one of the tricks you can use is to just recast it in logarithmic form. This is something you might remember from about 2 lessons ago. When you have 10 to the x equals 8, that's an exponential equation. X is in the exponent. But it can be recast as a logarithm. Remember that swooshy move idea, right? This raised to this power equals this. So 10 raised to the x power equals 8. So that is the same statement written 2 different ways. They contain exactly the same information. So 10 to the x equals 8 is the same thing as saying that the log base 10 of 8 equals x. And you've just solved it because, after all, that's a button on your calculator. You can take the LOG capital letters of 8, and especially if you can find your calculator way over there, way over there. Okay, so the log of 8, I hit the capital LOG button, and I hit the 8, right, and I'm getting something like 0.90309, which is approximately right. And if you want to check it, go ahead and go back to the original equation. Probably want to use the original equation in a different color. 10 to the 0.90309, so I'm just checking my answer here. What is that? 10 raised to the power of 0.90309. Boink! I'm getting 8.0000024. So it is very close to 8. It's within round off error of 8. Okay, so recast in logarithm form. I'm going to do that trick over here too. So I've got e to the x. Oh, somebody didn't finish the equation. Let's finish the equation, folks. Pretend that said something like e to the x equals 8. Okay, typo. It was supposed to be a finished equation. It's not supposed to be just e to the x sitting there. You can't solve something if it's just sitting there. You have to know what it equals. If you know that e to the x equals 8, okay, now we can solve it. So let's just pretend that's there. So pretending that was there, I'm going to recast as a logarithm, just like I did over here. Swooshy move. The base to this is equal to this. E to the x power equals 8. Okay, that's just the equivalent form of this statement. This is the exponential form. This is the logarithmic form. They both say exactly the same thing. But what's handy dandy about this form is we have a log base e button on our calculator. It probably has a capital ln on it. So ln of 8, and now I'm punching buttons to say what is ln of 8, and the ln of 8 is just about 2.079, like 442, something like that. So we solved it just by recasting as a logarithm. Now I'm going to check again just to make sure. If I take e and I raise it to the 2.079,442, and of course the more decimal places you use, the more accurate you can expect this to work out accurately. So where's my e here? There it is. Okay, 2.079. 442. This comes out to, I got 8.00000, like 3 something something. So it's pretty close. There's a little more round off error on this one, but it's pretty close. Okay, cool. That's your first trick. So again, when do you use your first trick? I would say if you have 10 to a power, you're going to want to use this trick because you'll end up with a log base 10 that you can play with the button on your calculator there. Or if you have an e to the x, you could do the same thing. Now, if you have 2 to the x, you theoretically could do the same thing, but then you're looking at a log base 2, which is not as convenient. So for that reason, we have a second trick that you can use. So if you don't happen to have 10 to a power or e to a power, you got something else, or especially in this situation, look at this. We got 2 different things to a power. I got a 9 to the x over here. I got an 8 to an x plus 5 over there. Okay, we need a new trick. Here's the new trick. You take the natural log of both sides of the equation. Just trust me on this. It's going to work. So I'm going to take the natural log of 9 to the x, and then I'm going to take the natural log of 8 to the x plus 5. And now you're asking, how the heck does that help? Well, it helps because, new color, or I shouldn't say but, I should say recall. We have a log property that says if you have something raised to a power, that power can come down front as a multiplier. Remember that thing? That's one of the big 3 of the log properties, the ones I call the big 3. So if I use that, that means that here, this x can come down on the ground. That's what we like. We don't want it in there. Come down on the ground. This is going to be great. So I've got x times the natural log of 9 on this side. And on the other side, I should put this in parentheses now, x plus 5 times the natural log of 8. X is on the ground. That's huge. That means we can solve for it. Now, you want to think of this as just some number times x, right? It's not a 2x, it's not a 3x, it's a log 9x, but it's an x term. On the other side of the equation, I should really distribute this out here. So x times the log of 8, which again is just some number times x, right? It looks funky, but it's just some number times x. And then I got plus 5 log of 8, which looks funky as well, but that's just some number, right? You can punch 5 times log 8 equals point whatever the heck it is. So you've solved equations like this before. If I had 3x equals x plus 6, you'd know what to do. You would subtract the x on both sides, and then you would divide. It's the same moves, So try to see this with me. I want to subtract this term on both sides. That x log 8 subtracted on both sides. So I'll have x times the natural log of 9 minus x times the natural log of 8 equals 5 times the natural log of 8. Okay, and I'm going to have to shrink this stuff up a little bit. Shrink yourself. Okay, cool. And in order to have enough room here, what do you do with this? Well, they're like terms. X times some number, x times some number. What you do is you subtract the numbers times x. They're like terms. What you might say instead is, hey, I think I'll factor out the x. That seems maybe a little more natural. So factor the x out, and you have a log 9 minus a log 8 equals a 5 log 8 on the other side. And the last thing to do is just divide both sides of the equation by that parentheses there. And so x will be 5 times the natural log of 8 on top, natural log of 9 minus the natural log of 8 on the bottom. And if you want to, you can push buttons and get a decimal out of that. But this is nice. This is exact form. I like exact form. Exact form preserves all the accuracy. It's like, the person who punches the buttons can decide how much they want to round it off. If you round it off, it's kind of like, well, what if I wanted it rounded off a little more? What if I wanted more decimal places? You went and took them away from me. You bum. So it's better to just leave it in exact form. So please just make a habit of doing that. Leave it in exact form. Anyway, what just happened there? We took the log of both sides. And then there was this property that said the x could, or the x plus 5 over here, could come down front. That was the magic of taking the log of both sides. And then it was really just a matter of getting x by itself, using old ways, our old ways. You might want to try this one yourself real quick. Do the same thing, take the log of both sides, and just, use that same property. Yeah, try it, see what you get. Ready? Here we go. Natural log of e to the x on this side, natural log of, what's this say, 3 to the x minus 1 on this side. Now, I could say, on this side, okay, bring the x down on the ground and take the natural log of e. But the natural log of e is just 1. How do we know that? Because natural log is a log base e. E to the what power equals e? The answer is 1. It's just a 1. So you could do that, but I'm going to invite you to say, well, wait a second. These are inverses, right? A log with a base of e, an exponential with a base of e. They're inverses. They just kind of cancel each other is all they do. So you hopefully can see right away that's just x. If you take the natural log of e to the x, you just get x. Boom. Boom. On the right side, no such luck. So we're going to have to take that x minus 1, bring it down as a multiplier times the natural log of 3. Okay, so let's do this. Let's distribute. So I've got x natural log of 3 minus 1 times the natural log of 3. I would like to have both of my x terms on the same side of the equation, so let's subtract x log 3 on both sides, like this. Notice that equals a negative log 3. I'm going to factor the x out like this. Really, I'm combining like terms is what I'm doing, but it kind of looks like I'm factoring out an x, right? And then I divide both sides by what's in the parentheses there. Negative natural log of 3 on top, 1 minus natural log of 3 on the bottom. That's a nice exact answer. It's beautiful. Beautiful. So there's the trick that you're probably going to use like maybe 95% of the time or even more, is you're going to use the take the log of both sides trick. This is our workhorse method for solving, like I say, the lion's share of exponential equations. Take the log of both sides. Trick 1 is kind of like a special case. If you happen to see 10 to the x or e to the x, you can kind of take a shortcut. You could take the log of both sides. It would work in that case too. I invite you to try it. It'll come out the same. So take the log of both sides. Now here's the thing. Look at this next one. First of all, it doesn't say take the log of both sides. It says switch variables. Why is it saying that? Why don't we just take the log of both sides? Well, the reason we don't take the log of both sides is, again, remember, take the log of the side. When we say take the log of both sides, we mean take the log of the whole side. So the natural log of e to the 2x minus e to the x, it's all in parentheses there. And the problem we have is there's no property. Wait. This isn't like having natural log of, m to the x or whatever. In this case, you can bring the x down in front and say x log of m, right? That's what we like. That's why we want to take the log of both sides. It's not working here. It doesn't work here. You've got two terms that are subtracted. It doesn't fit the form. And if it doesn't fit the form, you can't do it. You can't do it. It's not going to work, folks. And I hope you're not thinking in terms of, well, maybe I'll just take the log of this, and then I'll take the log of this, and then I'll take the log of this. No. You can never do things term-wise like that. If you're going to do the same thing to both sides of the equation, you have to do the thing to the whole sides. Maybe I'll just take a second and prove that to you real quick with, if I had 9 plus 16 equals 25, right? Yeah. If I took the square root of 9 plus 16 and I took the square root of 25, I'd get 5 equals 5, right? Right. But if I took the square root of 9 separately like this, now I've got 3 plus 4 equals 5. You just broke the equation. Okay, you never do those kinds of things. You never do things one term at a time. It's the whole side or nothing. Whole side or nothing. So we're not going to take the log of just this term and that term. Okay, we need a new way is what I'm trying to get at here. And so this new way is actually an old way that we just haven't used for a while. I think it was lesson 50 if I recall. The old, you see something and then you see something again, except in one spot it's squared. Remember this? W. Let's take that e to the x in the middle and give it a new name, w. What would you get if you squared w? You'd have to take e to the x and square it, right? Which you multiply the exponents together, you get e to the 2x. In other words, this is w squared. We've got w squared minus w equals 6, or I'll say minus 6 equals 0. So now I'm really happy. That's like an even happier happy. Yay, happy. Okay. We transformed our looked impossible to solve equation into a nice quadratic form. And so then we can do the old, let's go back to blue. Backed up blue. Now we can do the old, let's factor this here. Let's see, two numbers that multiply to -6, and I need to add up to, this works. There it is. And so I've got two solutions. W could be 3 or W could be -2. So that's pretty cool. Now I have to come back up to here and say e to the x is equal to 3 or e to the x is equal to -2. Right? Remember, once you've got your solutions for w, it's like, okay, go back and get x now. You said w was equal to e to the x. So 3 is equal to e to the x. -2 is equal to e to the x, right? So now we got to solve those over here. How do you solve this one? Oh, I can take the log of both sides. And remember, the log of e to the x is just x. So this is telling me right there, x is log 3. That's one of our solutions. Cool. What's the other solution over here? Well, if I take the log of both sides, I'm going to run into a problem real quick. You can't take the log of a negative number, remember? When you graph the things, the graph is over here, right? There's nothing over here when x is negative, and that's just kind of like you can't plug a negative into a square root. Well, you can't plug a negative into a logarithm either. You can't do it. So we don't get any extra solutions from there. So this equation just has the one solution, x equals the natural log of 3. So watch out for that, right? Every now and then you're going to be in a situation where you have to fall back on our old ways, like w substitution, whatever you want to call that, switching variables, putting it in quadratic form. You're going to need that sometime. Make sure that what you don't do is you don't take the log of this and the log of this and the log of this. No, two logs, the log of the left side, the log of the right side. If you can't do it, look for a different way. Okay. Hey, that's our logarithmic equations. So like I say, 95% of the time or more, this is what you'll be doing. You'll be taking the natural log of both sides. This will come up now and then, so make sure you remember that it exists, this w substitution type thing. And of course you can trick one. Yeah, it's nice, but technically you don't even need it, because if you take the log of both sides, those will solve the same way. Okay, that's our exponential equations all in one piece of paper. Cool. Logarithmic equations are going to take two pieces of paper, as I recall. Yeah, okay. Two pieces of paper, but they're not bad, really. The main trick for this is for logarithmic equations is swooshy move, which is another way of saying take your logarithmic equation and recast it as an exponential equation. Remember, natural log means log base e, and the swooshy move says we can rewrite that as e to the 4th power equals x. And guess what? You just solved. E to the 4th is a number, right? You can figure it out. 2.71828, raise it to the 4th power, get something. This is exact form. It's better to leave it like that, really. But that's a number. We solved. X is that number. Cool. Swooshy move. It works. It works here too, although this is a little bit different. Because remember what I was saying. We got two logarithms over here, so I can't just, how am I supposed to do a swooshy move with this one and this one? And it's not working the way that's set up, right? So actually, what we got to do here is we got to combine these first into a single logarithm using that property that says if you have a product, it splits up as adding two separate logarithms. We're going in the opposite direction. We've got two separate logarithms added together. We're going to combine them. We're going to go that way. So that's going to give us what now? We're going to have the natural log of, and I need to multiply the x times the 2x minus 1. And that'll equal the log of 3. I'll just leave that side alone for now. So I got the natural log of, let's just distribute and call that 2x squared minus x equals the natural log of 3. Now you could do swooshy move. Maybe I'll start to do swooshy move. You would say e raised to the power of log 3 is equal to this stuff. But by the way, what is e to the natural log of 3? E to the natural log of 3 is just 3. Remember, these are inverses. They cancel each other. Exponential base e, log base e, they cancel each other. If you put a 3 in to both of them like that, you're going to get a 3 out. It's just a 3. So what we got then, come on up here, is we've got that 2x squared minus x is equal to 3. Just 3. I'd invite you to bypass that. Whoops, wrong one. I'd invite you to bypass that and say, well, if this is a natural log and this is a natural log, then this has to equal this. In other words, if I'm plugging this into a natural log and I'm plugging this into a natural log and I get the same answer, then these things, it must be the same thing that I plugged in. The 2x squared minus x must be the 3. It has to be. I mean, you could almost picture, like, what if somebody had started with this equation and then decided they wanted to take the log of both sides, right? So anyway, if you spot that right away, it'll save you some time. Let's get back to where we were over here. We want to solve this thing. So we've got this 2x squared minus x equals 3. Well, that's a quadratic equation is what that is. Subtract 3 on both sides. Well, I can try to unfoil. Maybe this will work. I hope it'll work. If it doesn't work, I can always grab out my quadratic formula. But I think it's going to work. Yeah, that worked. So 2x minus 3 times x plus 1, right? 2x squared plus 3. Yeah, that works. And so we've got either, either 2x minus 3 equals 0, which would give us x equals 3 halves, or x equals negative, x plus 1 is 0, which would give us x equals, whoops, negative 1. I'm trying to write a negative 1 here, folks. Negative 1. Two possibilities. Now, here's the thing. I have to throw that one out. Throw away. Why do we have to throw that one away? Because if you look over here, this says the natural log of x, right? Natural log of x can't allow x negative. You can't plug a negative into a logarithm, in other words. So since you can't plug a negative into a logarithm, you have to throw that answer away. And so our only answer then is this one, x equals 3 halves. Okay, now that was still a swooshy move at heart, right? Swooshy move is usually what you do. It's just that we had some prep work. First we had to combine the logarithms. I look at this one and I say, okay, first we're going to have some prep work. We're going to need to combine those logarithms. Now there is a property of logarithms that says the log of, if you had an m over n, you could break it up as a subtraction like this, right? Seems like that property would be in play here. It's just that, these all have to be the same kind of log, right? And these are not the same kind of log. Oh, so we're not really ready to do that yet. First, I'm going to say but first, we need to make both of these into the same kind of logarithm, which means either that log 4 should be made into a log 16 or that log 16 should be made into a log 4. Doesn't particularly matter which way you go. I think I'll go with the smaller number. It's just a little less weird seeming. So first, use the change of base algorithm to convert that log 4 of x into a log base 16 of x. Remember how this works. The way the change of base algorithm works is you can take any logarithm in the world and change it into any other base in the world by doing this. You take, if I want a log 16, I'm going to take the log 16 of this divided by the log 16 of this. That's how it works. That's the change of base algorithm, which means I have to put a 4 here. I've just turned it into a log base 16. Now this is a number. I might be able to figure this out actually. Log base 16 of 4. 16 to what power would give you a 4? You'd have to take a square root, right? You want to be thinking of powers or roots. 16, I would have to take a square root. A square root means a power of a half. So this equals 1/2 down here. And so if I've got something being divided by half, that's the same thing as multiplying by 2. If you divide by a half, it's the same thing as multiplying by 2. So this is a 2 times a log 16 of x. Okay. So we can rewrite our equation now, because I'm going to take, in place of this log, wait a minute, I thought I wanted to go the other way. It's too late now. Too late. It doesn't matter which way you go, really. So, okay, now I'm playing with log 16s. Fine, whatever. At least they're both the same. That's the point. So I got 2 log base 16 of x minus log base 16 of x equals 3. Well, actually, this is working pretty nice. How can we combine these two together? Well, we're not even going to need this property. You know why? They're like terms. 2 of these minus 1 of these equals 1 of these. Oh, come on, let's write a little bit more neatly. 1 times the log base 16 of x is equal to a 3, right? They're like terms. 2 patterns minus 1 pattern is 1 pattern. And I can erase the 1, really. So log base 16 of x equals 3. Oh my gosh, we are so close. Because all we got to do now to solve it is that swooshy move. So apparently, 16 to the 3rd power. That's what x is. 16 to the 3rd power. Wow. Whatever that number is. That solves this equation. Wow, I wasn't expecting it to be that nice. That worked well. I'm happy. Boy, am I happy. Okay. Well, I knew there was one equation in here that wasn't going to be quite so simple. Yeah, so I guess it's the next one. Okay, you ready? The next one. We got to do the next one. It says big example 9 after all. Notice you get a whole piece of paper to do it. Okay. Why is this one going to be so big? Well, we'll see in a minute. First of all, we do have the same kind of logarithms, so that's not a problem. That's not a problem. So we can just go ahead and use that property that says if you have, the log of a product, you can split it up as adding 2 different logs, right? Remember that property? Of course, we're using it the other way around. We've got them added up already, so we can put them back together. So the natural log of, and then you would multiply the x times the x plus 1 is equal to 4. So I'll say the natural log of, and let's just distribute so it looks a little nicer, is equal to 4. Okay, so far so good, right? I combine those 2 logarithms into a single logarithm. Okay, time to do the swooshy move so that it's not, the x gets out of the logarithm that way. So natural log means log base e, and maybe I'll swoosh in a different color. So e to the 4th power is equal to what's inside here. And so that's telling me that e to the 4th power is equal to x squared plus x. Okay, see, here's where it gets a little hairy, because have you ever seen an equation like that before? Actually, you know what? I'm going to just switch the sides around. Remember, x is the thing that we're solving for, right? So don't let the e throw you too much. E to the 4th is just some number. I don't know what it is, but it's just some number. It's big. It's just some number. It's just a number. What we're solving for is x, okay? So the x, if you look at the x, you say, well, it's I got an x squared. Oh, it's a quadratic equation. If it's a quadratic equation, what I should do is set it equal to 0, and then either factor, I don't think so in this case, or grab out the quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac. That thing over to a. That's what we're doing here. So I'm going to switch colors now. So a is equal to 1, right? You just take that coefficient. B is equal to 1, right? You just take that coefficient. And C is equal to, well, C is equal to negative e to the 4th. It is what it is. So that means our solutions for x are, and maybe I'll just come over here now. X is negative b is 1, plus or minus the square root of b is 1, and it gets squared. Minus 4 times a is 1. Cool. times c is negative e to the fourth. That's what goes there. And on the bottom, 2 times a is 1. Pardon me. So what do we got here? Oh, shut up, you. I got a thing that has to shut up. Shut up. All right. So x equals negative 1 plus or minus the square root. That's a 1. Okay. Minus and a minus makes a plus. So it's going to be plus 4e to the fourth. Okay. And that's all over 2. Okay. Huh. Can we simplify this radical? I'm looking at this radical, and you really can't simplify that. It's not going to simplify, and the reason is because you're not really allowed to take square roots separately like this, right? That doesn't work. There's really nothing you can do with that radical. We can't simplify it. Okay, we can't, so we won't. Next question. Notice this is giving me 2 answers, and it's giving me x equals negative 1 plus some big thing, which is going to be a positive answer. But it's also giving me negative 1 minus, which is going to be a negative number of some sort. Can I plug a negative in? No. So keep your eye out for that kind of stuff. We cannot accept x being a negative answer, because again, you cannot plug a negative into a logarithm, so we'd have to throw that one out. And so, since we have to throw out the negative one, we only add. It's not plus or minus. It's only plus. Like this. Negative 1 plus square root 1 plus 4e to the fourth. That's all over 2. There is our one answer. So I said it was a big problem. I guess it wasn't super huge, although you did have to kind of mess around with plugging negative e to the fourth into your quadratic formula. So that must have felt a little different, right? That felt a little different. But that's our show for today, folks. We did exponential equations on page 1. Once more, taking the log of both sides is the main method you're going to use. Not quite always. Keep your eye out for switching variables. But logarithms, it's always going to be some kind of swooshy move at some point. You might have to use a log law to combine your logarithms first. You might even have to use change of base algorithm to make sure the logs are the same so that you can combine them. And then this one was funky. Had to combine our logs, but what made it funky is that when you did the swooshy move, you got this e to the fourth showing up in your quadratic equation, but that's fine. Just use the quadratic formula, trust it, and always make sure you double check. Don't take a negative x if it's going to mean plugging a negative into a logarithm. You can't accept it. Cool. I think that's that.